All right, good morning. Guess what? I fixed my reverse video thing. I had to change a binary code. It was easy. Yeah, I might actually have my technology working, like first try this morning, which would be a first this quarter. Alrighty, so let me start with talking about some ODP stuff. So let me run you through the ODP you just finished, and then let's go over the next one and make sure we're all on the same page. So 207, you were making this link program, this link function that links two nodes together, and that's you know, one line of code basically. Take your first node, set its next field to be equal to the address of the second node, right? So it's a one-liner, but there's a lot going on in that line, and there's a lot to understand in that one line. And getting that to work is good, but there's a deeper level question, which is, you know, what exactly does this mean? Why am I setting it equal to n2 instead of ampersand n2? Why am I doing n1 next instead of n1 star next or something, star n1 dot next, right? So all these details, these are the things you want to be trying to understand. But again, n1 is a pointer to a node. The arrow says move to the thing it points to. That's a node. Nodes have a field called next. So this highlighted part says the field called next in the node pointed to by n1, and we're setting that equal to n2. What is n2? It's the address of another node, right? It's a pointer, but we kind of think of it as the node itself, even though it's not. It's a pointer, right? But if we always use this arrow notation, we can actually think of n2 as the node, right? And just understand when we want to get the fields off of what we're thinking of as a node, we use an arrow instead of a period. And it kind of frees us from having to think too much about pointers and addresses when we're working with structures like this, right? And just think of it as a different way to access the fields in a user-defined structure. So I don't know if that makes sense or not, but that's kind of how I think about it when working on these things. So let's look at 208. So 208, you're getting a little fancier now. You're making a function named build, which links three nodes together into a linked list. So you're going to write a function build which accepts three integers and then makes a list that looks like this. So build takes, you know, int x, y, z, it returns a struct node. And what should that struct node be that it returns? It should be the address of a sentinel node which it has created. I can't just highlight it, but a new node that you malloc from memory, right? So inside build, what do? You make a struct node, you know, return value, which is equal to malloc, size of struct node. And then make yourself three nodes. Call it, you know, node X, node Y, node Z. And don't be afraid to be, you know, kind of explicit and wordy in doing this. So you can say struct node sentinel X node, Y node, Z node. So set yourself up, you know, a set of pointers to nodes to represent the four nodes that you need to build in this ODP. and then allocate space. And do that for xn, do that for yn, do that for zn. So now you have a set of 4 nodes that you have references to. They have no values in their fields yet, but how do you set these up? Well, let's say we want to set this x node's value equal to x, right? It's just x node data equals x. So you can set up the data fields for the x, y, and z nodes. The sentinel node, I don't care what you put in the data value, you can put in anything you like. And then do what you did in your link code, but do it a few times. Use something like, you know, your one line in the link code to set lists next field to the address of this node, which I'm calling xn. Set xn's next field to the address of this node. Setyn's next field to the address of this node, and set zn's next field to null. And then when you're all done, go ahead and return. So set up your next fields, and then just return the sentinel. Because the sentinel is the address of a struct node. So that's ODP208. And this is a definitely fun one to play with in GDB, because by just calling build and passing it, you know, 3 integers, you know, 1, 2, 3 or whatever, when you come back from build, you should be able to take that address that you got back and play with it inside GDB and see what's going on. So let's see. Myself in trouble here. Alright, if I accidentally show you the source code for build, just ignore it. Yeah, I can't do this. Anyway, play with it. Yeah, I'm not going to go through it. Go ahead, run it in the debugger, and do things like, you know, so make your main program have a struct node, set it equal to the return value from build, and then, you know, print out that sentinel node that you got back, and it should have a data field in the next field, and then print, you know, sentinel node arrow next, and that should show you the first node of your linked list, and so on. Let's see, quick question in chat: what causes a seg fault? So I forgot that I set up the main program for these so that you have to run them through the assess program. And if you just try to run them from the command line, it'll usually seg fault. Because it talks to the assess program interacts with it in a very specific way. It gives it certain inputs and so on. And sometimes secret codes and stuff like that. And if you don't do that, then the program, I don't have any error checking in those, it basically tries to use a value that hasn't been specified correctly. Generally, a seg fault is an access violation. You're trying to access a location in memory that's not accessible because it doesn't exist or because you don't have permission to access it. That's the high-level definition of a seg fault. So it's a segmentation violation, a problem with the segment registers that get you to memory. All right, so questions on ODP 207 or 208? And 208 is due tomorrow morning at 10. And looks like we got some 20 out of 20s on it, so presumably I loaded the question correctly. All right, so just a few final words on linked lists, final for now. We ended yesterday by noting that you can build a linked list that has backwards pointers as well as forward pointers. And if this makes your coding a little easier because you don't need to remember your previous node if you want to back up one node at some spot. And in fact, at any point you could back up, you know, as many nodes as you want. But let's look at some code for this. So suppose, you know, we'll throw some values in here. Suppose you're trying to insert a node. We'll call it new with a value of 25. So what do? You march through here until you find a node that's bigger than the node you're inserting. So let's call this our current node, C. And we want to insert this new node right before C. You have to do a few things. We need the previous node to point to this instead. And we don't have, you know, a P variable pointing to the previous one, but we can say C arrow previous, that gets us to the 20, next equals new. So that sets up this pointer. And then C arrow previous should be equal to new. So that sets up this pointer. And then new previous should point to the 20. Well, if I do C previous, I've got a problem because I just changed C previous. So let's actually do this before we change C previous. So let's set new previous equal to C previous. So that sets that up, and then new next is going to be equal to C. So you got to do 4 things instead of 2 things, but we didn't need to, you know, keep track of that prior node. But definitely watch out for this kind of thing. Right? Because the only way we can get to this is by using the previous field of C. We've got to do everything we need to do with that before we change this, right? Or, you know, make yourself not have to think as much. Set P equal to C previous before you start. So now this is my node P, and I can just say my usual stuff. P next equals new. New previous equals P. C previous equals new. And new next equals C. And it is a little less efficient, but there's absolutely nothing wrong with making temporary variables and using them. If it clarifies the code for you or for somebody else who's, working with this code down the road. And when we start doing things with binary trees, we're going to want to do this a lot. Because we're going to be, following links that are 3 or 4 things long. And it's a whole lot easier if you just set up temporary variables. You don't have to worry about, did I change C previous in the right place, or did I change it too soon? So yeah, and then this looks like add in PA2 except for the previous pieces. But the next pieces would be the same. All right, and the other thing we can do with linked lists is we can make them circular. And so we can have this last node point back to the first node. And if you're trying to print the contents of this list, you need to do something to make sure you don't print forever, right? So maybe you make note of the first node's address, and each time that you move forward, you check to see if the address of the node you're on is the same as that first node. But it's also common to have a list that you want to continue to go through forever and ever and ever. And I'll give you an example. Suppose you're an operating system and you're trying to manage a series of jobs that are trying to do things on your CPU. So you've got 200 things that want the attention of the CPU, and you need to farm out CPU time a little bit at a time to each process. So each of these nodes would be a process. And the idea is you're always going to look at the first node in here and give that a chunk of time, right? And then you're going to go on to the second node, and then you're going to go on to the third node, and so on. And after you've gone to the last node and you've given process N a chunk of time, what do you want to do? Well, you want to go back to whatever the next node is. So you're making a circular buffer, basically. And if process 2 gets a chunk of time and finishes, then we remove that from the list. And if a new process comes up, right, we go ahead and we insert it into the list. But the operating system just keeps moving down this list, and whatever node it's on, take that process, give it a chunk of time, let it run. When the time quanta is expired, just move on to the next next node in the list. And so that's a case where we really do want to just keep looping and going through the nodes in this list over and over and over. And this is more convenient really than having to constantly go back to the beginning of the list or something like that. And we'll see this in what we talk about next, which is stacks and queues. You can do doubly linked lists, you can do circular lists with or without a sentinel, you can do regular lists with or without a sentinel. And if you want to build a linked list without a sentinel, it's really not that different. So here's what we've been doing so far. So here's a linked list with 3 data nodes. There's a sentinel node, and then there's a 10 and a 20 and a 30. And here is an empty linked list with a sentinel. All right, if you get rid of the sentinel, this is what you have. Here's a linked list containing a 10 and a 20 and a 30. without a sentinel. And here is a linked list containing no nodes. Right? It's empty, it's missing. And this is why we use a sentinel node sometimes, because if we have a sentinel, an empty linked list still has something, which means we can treat this as a handle. Right? It's a handle to an empty coffee cup, but it's not fundamentally different from having no coffee cup at all, right? With this, if we have nodes, great. But if the list is empty, our linked list is basically null. And that's an edge case. And it takes some finagling to make that work. For example, your add function would need to take, you know, your current list, which is null, and then somehow change that to be not null. And we can't pass something to our function and have that something change unless we pass the address. So we need to start passing the addresses of these pointers to struct nodes, and it just gets really wonky. Now we're going to do that when we get to trees. We don't want sentinel nodes in trees. But for linked lists, it's just a little easier not to have to deal with a case where there's nothing at all. Right? There's also the added nicety that if we want to insert before this first node or delete the first node, our code still works. We don't have to deal with a case where you know, if this is the handle to our list and we get rid of that, we need to change our handle to be the 20, right? With a sentinel node, if we delete the 10, our handle is still the sentinel node. So it's a nicety, but there's nothing magic about sentinels, and there's nothing wrong with making linked lists that don't have sentinel nodes. But for learning about them, it's definitely easier to have them. All right. So any last questions on linked lists up to here? All right. So on to stacks and queues. So this is our next data structure, and if you've done Engineering 270, you've encountered stacks already. If you play older Magic, you've encountered stacks because you put your effects on a stack and you resolve them in reverse order of the order in which they're played. That's how my students learned about stacks. That's how I learned about Magic. So it was a fair exchange. Queues you've encountered anytime you go to the store and you have to stand in line at the cash register. You're in a queue. All right, so let me give you some first order definitions. So what is a stack? A stack is, think of it as, you know, a container that's open on the top, and you can only put things into this container from the top. You can only take things out of the container through the top. And so when you want to put something in here, let's say we're storing, you know, flat disks. So you can take one of these and put it into the top, and that disk 1, you know, goes down on the bottom. And now you put another thing in here, 2, and you put another thing, 3, and you put a whole bunch of these things. But we'll just do 4 of them. All right. So I put on, you know, this thing first, and then this, and this is the last thing I put in there. Now, if I want to remove things from this stack, the first thing I'm going to remove is the 4. And once I remove the 4, if I were to remove another thing, it would be the 3. And that 1 which I put on first is going to be the last thing that comes out. And so we use the acronym LIFO, which is last in, first out. The last thing we put on the stack is the first thing that comes out of the stack. So right now we've got two things sitting on the stack. If I were to take another plate, let's say it's 5, and put it on the stack, right, that would go right here on top of the 2. And even though the 2 has been sitting in there for a long time, if I now remove something from the stack, it's that last thing that I put in there. The 5 would come out before the 2. So you're removing things in the reverse order of how you put them on. Alright, stacks work really well for some things. They work really well for doing function calls. When you call a function, you have to save the return address that you want to come back to when you say return. Well, the operating system calls our main function, right? And that return address is sitting here at the bottom of the stack. And our main program calls, you know, some function that we've written, and the return address for that goes on the stack next. And that function calls printf, and the return address in that function goes on the stack here. When printf returns, we don't want it to go back to our main program. We don't want it to go back to the operating system. We want it to go back to where it was called from, which was this last address that was pushed on the stack. So stacks are used when we do function calls, because whenever you say return, you want to go back to the last place that you did a call from. So that's got a natural last in, first out structure. Stacks work horribly for refrigerators. Because here's what happens, and you can end up using a stack in your refrigerator, right? So here's the front of your refrigerator. And let's say you get, I don't know, let's say some orange juice, right? So you get orange juice 1, and you drink that, and it's starting to get low, and so you go to the store and you get another orange juice, and what do people do? They shove the new orange juice in here, so that orange juice 1 goes back here, and orange juice 2 is sitting here. And now you start drinking orange juice 2, and that starts getting low, so you go to the store and you come back with orange juice 3, and you push that into the fridge, and so this goes back here, and orange juice 3 is now sitting in the front. And you know, maybe you drink orange juice 3 before you get to the store, it's completely empty, so you take that out and throw it away, and you start drinking orange juice 2, but then you come home with a new orange juice and you push that in there. And 2 years later, you go to empty the fridge, and what do you find way back here in the back corner of the refrigerator? You find an orange juice from, like, you know, 1975, right? So that's stack behavior, right? The things that got pushed on first will possibly take a really long time to be removed. I don't do this, but once in a while I catch myself, you know, going down that path, and I force myself to, like, you know, put the new stuff in the back, but you have to pull out the old stuff and put it behind there. All right. So what would work better for a refrigerator would be a queue. And a queue is a first in, first out. And a queue would work well if when you got new orange juice, you could put it through the back of the refrigerator, and when you wanted to drink orange juice, you took it from the front. So what would this look like? Here's the front. Here's the back. Alright, so you come home with some orange juice, and you put it in the back, and every time you want to drink orange juice, you reach in and you take that one at the front. You go to the store, you get another orange juice, let's call it orange juice 2. Well, you shove that one in the back, so now orange juice 1 moves up, and orange juice 2 is behind it. Since you're taking from the front, you're still drinking from that first orange juice, the older one. And now, you know, you're feeling your hoarding impulses come in, so you go and you buy some more orange juices, and so this becomes, you know, OJ1, OJ2, OJ3, OJ4, OJ5, right? And these are the ones you just bought, and this one was a little older, and this one's very old. That's still the one you're going to be drinking from. And then when this is finally empty, and you pull it out and recycle it, what's the next one that you're going to drink from? It's OJ2. So a FIFO, you're removing things in the same order in which they were put into the structure. So first in, first out. The first thing that you put in here is the first thing that comes out. This is how we want checkout lines at the store to work. Right? You have a checkout line. You have a cashier. People come in this end and they leave that end. And the first person in line is the first one who's taken care of. Whoever comes in second should be the second person who gets taken care of. And if there's 5 people in here and another person comes, they don't get to the cashier until all 5 of those people have left the queue. So that's an in-order processing. And FIFOs work really well for some things in the system. For example, for scheduling jobs. If you have 5 processes that are waiting for execution on the CPU, and somebody says, you know, let's run this program, so now you've got a 6th process, you'd really like that 6th process to run after those first 5 have already gotten their share of CPU time. If you did this with a stack, then every time that somebody decided to run something new, they would suddenly get, you know, the CPU, they'd be next in line for the CPU. And the older jobs that have been waiting for a while might never get a shot at execution. So LIFOs and FIFOs, stacks and queues, they pop up in lots of different places, and sometimes one makes sense, sometimes the other. All right, let me give you another example of a stack. So you sit down to do your homework, and your homework requires you hop onto Canvas to see what the current homework assignment is for 215 or something, right? So you open your browser, and here's Canvas. All right, and as you're going through, you see an announcement, right, in the class website, which says, here's a job opportunity. All right, you were at this point on the Canvas page, and you say, I want to go look at this job opportunity. So you click on that, and now you open a new page, which shows you jobs, and you start reading that. And over here is some, you know, advertisement for a new gaming computer that's available somewhere, and you click on that, and now you're on a page that's talking about games, and you start looking at that, and over here is a review of a video game, and so you click on that, and you're going down this path, right? We were on this page, then we jumped to this page, we got down to here and went to this page, we got down here and went to this page. Eventually you're going to hit the back button. And the back button is going to take you not here, not here, it's going to take you back to where you were right before you clicked on that review. So this is going to send us over here, and when we hit the back button, we're going to come back here. And we're going to continue reading our games page, and maybe we'll see, you know, advertisement for some sort of sale on cartridges, and so we'll click over there and we'll read that and we'll come back here, and eventually we're going to finish using this games page and we're going to hit the back button, and it's going to take us back to our page where we're reading about job announcements that have been posted for the class. And eventually we're going to get to the end of that and we're going to hit the back button and we're going to come back to Canvas. We're going to be like, oh yeah, announcements, and we'll read the next announcements and it'll say, you know, important change on PA2. And so we'll click that, and that'll take us to the page that describes PA2, and we'll see the change says you have to use the bunny rabbit function. And we'll say, I don't know what the bunny rabbit function is, and so we'll go to Google. And we'll start reading Stack Exchange discussions about the bunny rabbit function. This is a stack, okay? It's a stack because anytime that we leave our current page and we go somewhere else, when we hit the back button, we're going to come back to where we were most recently. When we come back from PA2, we're going to go back to Canvas. And as we follow, you know, this rabbit hole of following these links and clicking down deeper and deeper pages, the return to our original spot gets further away. Okay, so this is definitely a last in, first out structure. And we do this in life, you know, as well as browsing. So you're making dinner and the cat needs food, so you stop dinner and you feed the cat. And while you're feeding the cat, the can of cat food is empty, so you have to open a new can, so you stop feeding the cat and you go to the pantry and get another can of food, and so on. And eventually you unwind all of that and you come back to making dinner until the phone rings. And then you stop making dinner and answer the phone, and so on. We tend to live in this kind of stack-based way. And that can be helpful or not helpful. But sometimes we do things like a FIFO. So when I'm feeling very disciplined about my work, what do? I start grading. And while I'm grading, an email comes in. Well, I put that in my queue. I don't stop grading though. I keep grading. I'm going to grade until I'm done grading. And while I'm grading, my music ends. But I'm not going to go put on new music. I'm going to finish grading. And so new things that come in go into the back of the queue, and I always process things from the head of the queue. And if I'm really, really super FIFO-oriented disciplined, when I finish grading, I still don't put on new music. I take care of my email because that was next on my queue. And only after I finish my email and my music comes up to the head of the queue, then I go ahead and I put on a new playlist. Alright, two fundamentally different approaches to things. But they can be implemented almost the same way. Alright, so questions about the structures themselves, the sort of higher level view of what these structures are. Making notes. All right, let's talk about these structures as abstract data types. So you have a stack. What do you want to do with it? We want to be able to initialize it. Pretty much any time we have a data structure, we're going to have some kind of initialization function to basically tell the code that's managing the structure, hey, I want a new one of these, whatever it is. I want a new stack. And keep in mind, you know, when you're writing code to implement a linked list, for example, a main program should be able to create more than one linked list at a time. You should be able to make 3 linked lists if you want, and have them be totally independent of one another. You could create an entire array of linked lists if you want. You could actually create a linked list of linked lists. So you always need an init function whose job it is to basically give you a new structure of whatever type we're dealing with, and that does whatever initialization is necessary. So init would be a function that basically creates an empty stack and gives us some kind of handle to it, some way to get a hold of that stack. And then we really don't have a whole lot of options. We might want to add something to the stack. And this is an operation called pushing. So push data says add data to the stack. We also might want to remove something from the stack, and that's called popping. And we're removing from the top of the stack, because that's all we ever do with a stack. We pull off from the top, we insert into the top. So push and pop are the 2 main actions that we do with stacks. Push adds something to the stack, pop removes something from the stack. And you might want some other niceties. You might want an isEmpty function, which tells you if the stack is empty. In other words, is there anything there that I can push? And you may want an isFull, which says, is there any room left to push something? Depending on how you implement your stack, it might have a fixed size, or it might be allowed to consume however much resource it needs. And so when we pop, we need to deal with the possibility that we're trying to remove something from a stack that's empty. And when we try to push, we need to deal with the possibility that maybe there's no space left to push anything more onto the stack. Maybe we're out of memory. But first order high level view, right? Mostly what we do with a stack, we initialize, we push, we pop. And that's pretty much it. We really don't, deal with the stack other than the thing that's at the very top of the stack, the last thing that was put in. And we either put something else on top of that, or we pull that thing off. So that's a stack. A queue is basically a similar pair of functions, but we name them differently. So we still want some kind of initialization. But instead of pushing, we say we insert. And instead of popping, we say remove. And we might still have an isEmpty and an isFull. And so insert pushes something into the back of the queue, remove takes something from the front of the queue. And I'm going to fix some terminology here. And this is pretty vital. So we'll put a typo in it. So if this is our queue, and we insert into this end, and we remove from that end, we name the two ends of this queue or this pipeline. So this is called the head, and this is called the tail. And there's some ambiguity in the literature as to the use of the terms head and tail, but I'm going to try to be absolutely consistent in this course. We're going to insert at the tail, and we remove from the head. So the head of the queue is where the next thing is that you should remove, and the tail is where you're going to put the next thing in. Right, and remember this is a FIFO. So our first entry goes into the tail, and that's going to be the first thing that's removed. And when we think of this, you know, as a checkout line in the store or something, we kind of picture, you know, you insert at the tail and you move up as far as you can. And then when we remove something from the head, everything moves up. And that's a good kind of working model for how these things are laid out, but in practice that's not how we actually implement them. But you can think of it as, you know, insert and go up to you know, the first available spot in here, and when something gets removed, move everything up. So the first thing into the queue will be sitting right here at the head, ready to be removed. The third thing will be sitting 3 spots back from the head, and we'll wait until you remove 2 things in front of it before a remove will take off that third thing that you inserted. All right, is that clear, confusing? Questions about that? I really want you to understand these things from an operational level before we start talking about implementing them. So I gave you a high-level view. We talked about some examples of using stacks and queues, and now we're looking at them as abstract data types. So this is a main program's interface. Data go in, data go out. There you go. So a main program working with a queue, it would say, you know, initialize a queue, insert some data, remove some data. And a stack, right, initialize a stack, push some things onto the stack, pop some things off the stack. And almost every CPU that you encounter actually has instructions called push and pop. And it has a stack pointer that keeps track of where the top of the stack is. And that's usually implemented in hardware on most CPUs because stacks are so fundamental to what we do. They're fundamental to doing function calls and returns. They're fundamental to setting up local variables, passing information to functions, and so on. So these we will write these, you know, in C, but they're actually assembly language instructions on most architectures. Some architectures also have assembly language implementations of queues, but that's less common. All right, so the next step is to move below the level of an abstract data type and think about how do we actually write these functions? What should these functions do? And there's a bunch of ways we can answer that. We can create a stack using a linked list, and we're going to do that first. We can create a stack using an array and an integer. right? We can always create a stack using a text messaging app and a friend on a desert island. And when we push something, say, hey, here's some data to push, and we want to pop, say, give me the last piece of data that was pushed. And as long as all of that is wrapped inside, a standard interface to a main program, somebody who's written a program using these function calls, their program's going to work perfectly fine, whether we're implementing these with a linked list or an array or a friend with a cell phone, right? That's the goal of having an abstract data type. You have this firewall between the user interface to the data structure and the actual implementation of the data structure. All right, so we'll start implementing these tomorrow, starting with linked lists, and we'll do that for stacks and queues, and then we'll implement using arrays, and then we'll talk about some coding details. All right, have a good one. I will see you tomorrow.